Hello, today we will look at some applications of ordinary differential equations, namely ODEs of order 1, because we already looked at them a little bit. Let's start with something that you already heard, most likely. People sometimes say that the more money you have, the more money you make. So let's have a look at it, and we will use Y to denote the amount of money that you have. So that's our wealth. And of course it changes in time, most likely. So Y is a function of time. The more money you have, the more money you make. Okay, what does it mean, making money? Well, when you make money, it means that your wealth increases. So the money you make actually refers to the increase of your function, or in other words, the rate of increase, in fact, and that's the derivative. So the more money you make translates mathematically into the derivative is larger. So the more money you have, the larger the derivative of your money. Okay, so far so good. The more money you have, the larger the derivative. Well, there should be some correspondence. Now, which one? That's a good question. Let's try something very simple. Proportion. There is some proportional constant times how much money you have. Yeah, this could work. The more money you have, the more money you make. That sounds reasonable. Now, what we just did, we created a mathematical model for your wealth, for your money. This is a mathematical equation, and when you write something like that, it creates a virtual mathematical world. So mathematicians very often create artificial worlds with its own rules, which are usually given by some formulas, and then they try to investigate this world, hoping that they will learn some insight into whatever things they are modeling. Here we are modeling money, so when we look at this model using mathematical tools, we will perhaps get some insight into money, which is a nice thing, of course. So let's have a look at this model. That's an ordinary differential equation, definitely. It's of order 1, definitely, and it's separable. That's a good news. Let's separate. We want to divide by Y, definitely. So here is a side note. Y equal to 0, that's a stationary solution. Having this out of the way, we should also look at restrictions. Do I see any restriction? The answer is no. So I can expect solutions everywhere with a bit of luck. Here we go. We separate. We divide by Y, and I visualize this as dy over d, let's say dt, because it's time. So dy is left here, and I move dt to the right. Now I attach integral signs, and we are happy. We have a nice separation, and we keep going. I integrate. I integrate. I look at it and say, well, we saw this one before. That's the problem or the differential equation with logarithms. So we know that we should take the exponential of both sides. Now we replace the absolute value with plus minus and put it here, but then we multiply the whole equation by plus or by minus and it moves here. So y is plus or minus e to c times e to rt. And finally, we will introduce a new constant here. Yt is equal to d times e to rt. And because this is an applied problem, we will use the applied condition. We start at time 0 and see what's happening with our money, or whatever else. We will get to it soon. Now, we commented it before, so let me just remind you that this constant over here, this little object, can never be 0. But if we put 0 for d, we will actually incorporate the stationary solution. So this is really the general solution. Very nice differential equation. Very simple. And the outcome is an exponential based on this constant r. That's the proportional constant. So this all nicely fits. Now, it actually fits even better. Initial condition. Let's see that we know what's happening at time 0, because we just count our money. No problem there. Now, when we substitute 0 for time, this becomes 1, and it means that d should be actually y0. That's wonderful. We are actually able to provide a nice formula if you know the initial data, which means how much you have at the start and what is the proportional constant, then you can immediately write down the solution. And that's the overall picture that we want to see. We have a differential equation. We have an initial condition. And from this we get a nice solution. This is actually called the exponential growth. Now, although this is very simple, it actually finds its applications. We will talk about it a little bit later. And in some fields, they are sort of trained that when they see an equation like that, they immediately write the solution because they know it, they use it a lot. Okay, how about our money? Well, if our money really is described by this formula, then they should grow exponentially. Does it fit? That's a good question. When people make a mathematical model of some situation, of course they use some insight to form the right formula. But sometimes this is not quite obvious which formula is the best. According to, well, okay, we are making money, so R is positive, so we should expect that our money will behave like this. Does it work? I am not quite sure. So perhaps this model is not exactly faithful. So there are two sides to mathematical modeling. The model, when you solve it and when you analyze it, all this work can be absolutely correct. So the mathematical part can be correct, and mathematics has tools that sort of help you to do correct things, which is nice. But then there is the second question, this one is more important perhaps even, that the model should be faithful. So what people do, they do verification of the model, they look at the predictions, they match them against the data that they have, and sometimes they find out that actually the model is not really very good. For instance, I strongly suspect that wealth of people does not grow exponentially. I think that's too much. So perhaps there should be some other function, perhaps square root of y. Or perhaps some people get even richer, they get rich faster than exponential, then perhaps there should be y squared or some other function. I don't know. So that's something which is out of the realm of mathematics. Somebody has to come up with the right formula to describe the part of the world. So creating mathematical models and verifying mathematical models, that's for specialists. And here we will be interested more in how to handle those resulting models. Okay? This is an exponential growth, a very nice simple model. So let's ask some good questions. For instance, what good is it for? Are there some situations where the change in their quantity is proportional to the quantity? That's a very good question. Actually, there is one such case, and it's very useful and very nice. And it's the spontaneous radioactive decay. The world is composed of atoms, you learned about it at school, and some of those atoms, some elements, they actually decompose, not by our forcing somehow, like in a nuclear power plant or an atomic bomb, but naturally, they sort of feel like it. And this usually happens probabilistically, which means that every atom, once in a while, rolls a die, and if there is a 6 on it, it just decomposes, something like that. So let's say that you have some amount of this material which is decomposing spontaneously, which is decaying happily, and you are interested in the amount, how it changes with time. So y now is the amount of this material. It could be a number of atoms, which would be a very large number, or it could be, let's say, the weight in kilograms. Now, if every atom within a given time span decomposes with the same probability, then how many atoms did decompose? Well, the more atoms you have, the more of them actually decompose. That's a nice direct relationship. If you have twice as many atoms, then within a given time, you have twice as many decompositions, and so on. So this fits the radioactive decomposition really very, very well. Now, radioactive decomposition definitely has R negative. We didn't talk about it too much earlier, but R can be anything in the exponential growth. And in this case, when you have atoms, they decompose, so the number of atoms or the weight of your material decreases, so the derivative should be negative. Here is a positive number, how much you have. I multiply it by a negative number, I get negative derivative. So that's how I see the composition or decrease in the material by taking R negative. How does it look like? Well, we all know how the exponential looks like. Well, where is it? Here. That's the formula. We know how it looks like when R is negative. It looks like this. Here is Y naught. That's where you start. Here is time. And it goes like that. So that's a typical shape for anything which satisfies this condition or this formula with R negative. In particular, carbon. The whole world, including me or you, is composed, among other things, of carbon. It's called C, I think. Now, there is a special version of carbon. The usual carbon is C12, and it's fairly inert. It stays around. But there is a special form which is called C14, and this one is not really happy to be here. So after a while, it decomposes. At the same time, it is also created in the atmosphere by cosmic rays or things like that. It comes from the outer space. So what is happening? We have some C14 in us, and it decomposes, so there is less and less of it. But at the same time, we are getting it in because we are breathing, essentially. So as long as we breathe, there is some balance, some Y naught. That's the amount of C14 that we have in our bodies. Then one day, we die, and we stop breathing because, I mean, most people, when they die, they stop breathing. Zombies don't breathe either, whatever. So we can rely on that fairly well. And once we stop breathing, there is no more C14 coming in. So whatever we had in us starts decomposing like that. So we die, they put us somewhere in the ground, whatever. And 300 years later, somebody digs us out, some archaeologist, most likely. And what they do, they measure how much C14 we have in our body, and they get this. And then they look at the graph, and they say, okay, this is how long we have been dead. Nice, neat. And that's something which is called radiocarbon dating. And that's what they do when they dig out something which is, let's say, 1,000 years old, 2,000 years old, and it must be organic. It must be something which was breathing while it was alive, including trees, lovely flowers, animals, of course, things like that. So that's what archaeologists do. Of course, there is a trouble, because you can see, and we will be talking about this in numerical analysis a lot, there is usually some error over here. When you are measuring how much C14 there is, you don't get a precise number. Your measurement is never precise. And when you translate it into the answer, you get a certain uncertainty. So there is some error in your answer as well. And you can notice that if this thing is really old, and your measurement is here, then the same error over here, I'll mark it so that it looks the same, translates into much bigger error over here. So for older things, the margin of error or the quality of the answer that you get is much lower. And as you keep going into the past, it gets worse and worse, and then it's worthless, essentially. So using this C14 dating, you can get something like, I don't know, 10,000 years, 20,000 years back, which means our hairy forefathers. I mean, not so hairy. They already lived in caves, and they had some tools, Neanderthals and so on. But if you want to see dinosaurs, you're out of luck. So for dating dinosaurs, they use some other elements, not C14. But anyway, this is actually something very useful, which is being used a lot in some fields, and it is all based on a very simple differential equation, exponential growth. And it really, really works well. Let's think of something with R positive. Okay, the money probably doesn't work really that well. I don't see money like that. So is there some other area or some other, let's say, phenomenon which would work like that? Well, let's see. Let's say that you have rabbits. When you have rabbits, they multiply, and common sense says that if you have doubled the rabbits, then within a certain time, you get double the baby rabbits. And if you have 5 times more rabbits, you have 5 times more baby rabbits, and so on. This seems to work. The amount of rabbits is proportional to the amount of the breeding. And that's something that they use in biology, exponential growth, very popular in biology. This R is then called the breeding constant, for instance. And you get exponential explosion of rabbits. That's something that they actually saw in Australia. When the first rabbits were introduced, I think there was something like 24 of them. And within a few years, there were rabbits everywhere. So this exponential growth, quite good. You can also fit the exponential shape to the number of people on the Earth. When you look at the population growth, up until, let's say, the end of 19th century, this actually fitted quite well, because there is another aspect of mathematical modeling. There are some constants over here. For instance, when you look, well, we don't know how many people there were at the start. Some people think that 1, perhaps, or 2. And I don't want to make fun of it, we simply don't know it. So we have a formula here which has 2 parameters in it. And now we have some hard data. Of course, we don't know how many people there were at time 0, because we don't know what time 0 is. We just have some data. So what we do, we try to choose the parameters so that the curve has the best fit possible. And then based on that, people make predictions. So we should be quite sure that we know what we are doing. Anyway, people tried it with human population. This is called population dynamics. They tried it with rabbits. They tried it with bacteria in a petri dish. If you put some bacteria in a petri dish, let's say doctors do it all the time when they are investigating what people have in their throats or whatever. And the bacteria start multiplying, and they exactly follow the exponential growth. So this is a very good model, but it works only up to some time. It turned out that human beings or bacteria, they all have this property that after a while, the curve starts going differently. What's the problem? Well, the problem is that there is a lack of resources. So we will need a better model when we take into account how many resources we have and so on. But for some parts of development, the exponential growth is actually fairly good, and it has the advantage that it's simple. That's a big advantage of this model. Okay, before we move to something more advanced, something which takes care of this part, let's play a little bit with this model, because this one is quite flexible. We can do some things with it. Here is one. Let's say that we have those rabbits, and let's say that there is lots of area for them and lots of food for them so that they can actually multiply exponentially. But every day we eat 1 rabbit. So there is a constant removal of the population. Why H? H because of harvesting. This is called exponential growth with harvesting. What we get is actually a fairly simple situation, because we can solve it in exactly the same way. So we divide, but now we have to divide by this whole formula. Ry minus h integral dy, and on the right integral, wow, when I divide there will be just 1 dt. Now, do I feel happy about integrating? The answer is not quite, well, it's easy, but I will have to take care of this multiplicative constant. So it's easier if I put it here and also here. And then my situation is quite simple. Now it fits nicely. When you do the substitution, you will see that it will work out really well. So here is the left-hand side integral, and the right-hand side integral. And it looks really, really similar. Okay, I'm going to put the exponential here, then I get rid of the absolute value, and I get Ry minus h is equal to plus minus for the absolute value, e to c times e to rt. I introduce constant d, but perhaps before I do it, I will get rid of this r. So I divide everything by r, and there will be e to c divided by r, and then I introduce a new constant. So let's see, there will be constant d times the exponential. Here will be y, because I divided by r, and I move this one to the right, and I get this. Okay? So we can see that this is actually a shifted exponential. Now, depending on the sign of r, this could be an exponential which goes away from this value, and if r is negative, then it goes towards this value. So all kinds of things are happening. This constant d can be again determined from the initial condition. Well, let's try it just out of curiosity. So let's make a little side note here. What happens when time is 0? When time is 0, then the harvesting amount dividing by the breeding constant plus, and I put 0 here, so plus d should be the initial value. So we look at it and we say, okay, d must be y naught minus h over r. That's the conclusion. So we have a formula. If we know the initial amount, then the development goes like that. Plus y naught minus h over r e to rt for t greater than or equal to 0. So this is what we get with the exponential growth with harvesting. And now we can ask some good questions. Okay, we have rabbits. So rabbits, they are multiplying. So r is positive. Definitely r is positive. What's happening here? Well, h over r is the basic level. Now, if r were negative, then this exponential at infinity would be 0. So the solutions would be going towards this value. But for rabbits, r is positive, so this exponential goes to infinity. It goes away from this value, but it's multiplied by a certain factor here. And there are two possibilities. If this factor is positive, then the solutions just go away. So essentially, we have exponential rabbits in Australia. We start eating rabbits regularly, but they still breed like crazy. They breed like rabbits, let's face it. When does it happen? It happens when this constant is positive. Y naught minus h over r should be positive. What does it mean, positive? Well, let's say that it means that h is less than r times y naught. How do I translate it back from the mathematical model? So this is the model of Australian rabbits that we use for breakfast, okay? Well, the conclusion, if I translate it back into real life, is that my harvesting was too small. And therefore, those rabbits are still breeding. If the harvesting is stronger, then this constant would become negative, and the population would go like that. It would die out. And finally, there's the value when h is equal to r y naught, then this becomes 0, and you simply have a constant number of rabbits. That's the special case. H is equal to r y naught. So you can see that the behavior of the system is very, very sensitive to the value of harvesting. I'm not going to talk too much about it because people don't really use the exponential growth with harvesting all that much. As I said, it only works if the population is free to multiply, which in nature does not happen all that often. But it does give us some insight. And this is actually a fairly useful observation that sometimes the differential equation that you have, or the mathematical model, depends on some parameter, and you are perhaps free to influence it somehow. And it may happen that the behavior of the model or the behavior of the solutions depend on the parameter in a nice steady way, sometimes. But it may also happen that the behavior changes abruptly if you change the parameter just by a little tiny bit. Here there is a very tiny difference in age between the exponential growth and between the extinction. Very tiny step. And something like this is called bifurcation, and there is a special theory about it. These systems are very interesting from a mathematical point of view. The behavior is really sensitive. Of course, if you are a biologist, you definitely want to stay in this range. But as I said, this is too simple for such kind of, let's say, reasoning. Okay, let's try another small change of this exponential model. Imagine that you are in the desert. So there is a temperature, let's say, TD, which could be something like 50 centigrades. How much is it in Fahrenheit? 120 something, 122 I think, whatever. Anyway, it's a lot. So you want to feel better, so you take out ice cream from your freezer, let's say mint chocolate chips. That's my favorite. Why mint chocolate chips? Because it tastes great. And second, and that's big advantage of it, if you put it to the freezer, it does not freeze bone hard. It does not become like a stone. So when you take it out of the freezer, it's still a little bit soft and you can immediately start eating. That's what I like about it as well. Anyway, you got your mint chocolate chip. And what's happening, of course, this heat from the desert starts going into it and the temperature starts going up. Let's talk about the temperature and let's call it Y. Why? Because it's traditional in differential equation field. So change in temperature, that's a good question. How is the temperature changing? Well, there is this exchange of heat between the ice cream and the desert, the surrounding desert. Now, the ice cream is too small to cool down the desert, let's face it. So the desert will always be something like 50, let's say, if you do it for 1 hour. Yeah, it doesn't change, so it's 50. But the ice cream will start getting warmer and warmer. Now, this is perhaps not a good ice cream because there would be something like a gradient of temperature. It would be colder inside compared to the outer layer. So let's just say that it's a very flat piece of ice cream. And now we can imagine that the temperature is the same everywhere, okay? My camel sat on it accidentally or something like that. So we have this ice cream where the temperature is the same everywhere and it exchanges heat with the surrounding environment, which is at 50 centigrades. Now, what is the change in temperature? That's a good question, and there is something which is called Newton's law of cooling, I think it is. And it says the transfer of heat between those two environments is proportional to the difference of the temperatures. What's the difference? Well, 50 on the outside and Y on the outside. That's the difference in temperatures. And that's a very nice growth, which is remarkably similar to this one. And again, we can solve it easily. So I'm going to divide. There is this stationary solution business also here. This is actually a stationary solution. And by the way, this equation is autonomous. And when we look at it, we can see that this stationary solution is not stable. Definitely unstable. Okay, let's have a look here. I can see a solution. Y is equal to 50, that's a stationary solution. And otherwise I will just divide and I get dy over 50 minus y is r dt integral logarithm 50 minus y is equal to rt plus c, and I have to be careful because I'm integrating here and there's a minus sign in front of y, so it jumps out like that. You do the substitution if you don't see it. This is basic calculus stuff. Okay, I move minus to the right. I get rid of the absolute value and I get 50 minus y is equal to plus minus e to negative c times e to negative rt. So far so good. I introduce new constant, let's call it d, and then I play with it a little bit and I get that yt is equal to 50 plus d e to minus rt. T non-negative, let's say. And again, I could incorporate the initial value into it somehow. Here is how it looks like. This is the stationary solution 50. And now R is positive because it's a proportional constant for the physics law, for the Newton's law of cooling. Which means this is negative actually. This is an exponential which is disappearing. And it goes like that. Here is my ice cream out of the freezer and the temperature goes like that, exponentially, or like that. If you actually boil the ice cream for some reason, terrible, okay, I'm not going to think about it. So if you boil the ice cream, it will go down with temperature to the nice cool 50 centigrades in the desert. So that's how I see the development. Yeah, again, it's an exponential event. In physics, many laws have a similar shape and then you can expect exponentials. I would say that this is a stable stationary solution or stable equilibrium. And I would be right. we can do the analysis of the slope field here. This is very simple. What's the sign here? Well, it's determined by 50 minus y. If y is more than 50, you get negative sign, decreasing. If y is less than 50, positive sign, increasing. Very nice stationary solution, which is stable. Okay, that's it concerning the exponential growth. I think I milked it enough. Let's pass to something more sophisticated.